Problem number 13. A ballistic pendulum is designed as shown below. A uniform ball of mass m and radius r is attached to a massless rigid rod, so that its center is distance L from the ceiling. The ball has a small tunnel hollowed out. A small block of mass m and the speed v goes into the tunnel and collides at the center of the ball perfectly inelastically. Subsequently, to what maximum height does the block rise? Solution for problem number 13. First, let's use angular momentum conservation, because during this collision the angular momentum is not changing, and we can write equation that initial angular momentum for this small mass m equal mvl, and it's going to angular momentum for whole system rotating around ceiling point, which is I omega. I, it's a moment of inertia of whole system, this pendulum plus this mass, and omega is angular speed. Now let's write equation for angular momentum of this system. The equation for this angular momentum, the expression for this ball around the center of mass, which is 2/5 mr square plus ml square due to parallel axis theorem, and plus ml square, that's from this small mass m, and finally that will be 2ml square, and we can write this equation. So it means that omega equal mvl over I. Let's write expression for kinetic energy, because after collision this kinetic energy go into potential energy for whole system. That will be 1/2 I omega square, and after insertion of this omega we will have this expression, and this must be equal to 2 mgh, which is potential energy for whole system. Now let's use expression for I, put it here, and find that h equal this expression. Let's answer D, and that was a solution for problem number 13. Problem number 14. A cylinder of water is suspended in a space station. Under the influence of surface tension, the cylinder splits into droplets. After a short time, viscosity causes the droplets to settle into static shapes. Neglecting the effect of evaporation, compared to the original cylinder, the final set of droplets will have next one. Solution for problem number 14. Because water is almost incompressible, the volume stays almost exactly the same. During the process, energy is dissipated due to viscosity, and the energy due to surface tension is proportional to the total surface area. Thus, the surface area must decrease. That was answer E, and that was a solution for problem number 14. Problem number 15. 5 astronauts are orbiting Earth in a low circular orbit. They decided to go around the planet following the same orbit but much faster. To set a new record for obtaining Earth, 4 of them thought that they could quickly increase the velocity, then use a jet engine to maintain an orbit of the same shape. In the first 4 choices below, the red arrow denotes the direction that fuel will flow out of the jet nozzle. The fifth astronaut was skeptical about such a possibility. Who is right? Solution for problem number 15. The centripetal acceleration required to follow a circular orbit is, if the speed is increased, the inward acceleration must be increased, so the engine should be pointed outward to provide an inward force. So that's answer B, and that was solution for problem number 15. Problem number 16. A uniform rectangular block is in static equilibrium on an inclined plane and experiences gravity, static friction, and normal force from the plane. Though gravity acts on the entire volume of the block for the purposes of torque balance, it is equivalent to a single resulting force acting at the block's center of mass. Similarly, while the normal force acts on the entire bottom surface of the block, its torque is equivalent to a resulting force acting at a single point. Which of the following best shows this point? Solution for problem number 16. Consider the point of contact between the block and plane directly below the center of mass. Gravity effectively acts at the center of mass and thus exerts no torque about this point. The friction force points along the plane and thus also exerts no torque about this point. Therefore, since the block is in static equilibrium, the net normal force must effectively be applied at this point, yielding choice B. So that was a solution for problem number 16.